10. Now let's say, suppose Q is a function such that Q3 equals 14. Then A, they ask you name one point on the graph of y equals 5 times qx. Okay, to name this point, let's see how we can do this. Okay. Here you can say we can calculate y. You can say y3 when x equals 3. You get 5 times q3. So then get this 5 times 14. This gives us 70. So that means we can get a point that's x coordinate, that's 3, y coordinate, that's 70, right? So we can get this point on this graph. Now let's name one point on the graph, y equals qx plus 5. Then you can still do this. Then this one will give you q3 plus 5. So this one equals 14 plus 5 give you 17. So that means in this graph we have a point x coordinate that's 3, y coordinate that's 17. Now C, you can see we can do this one. You need to put y value equals what? Should be -2. Okay, then this is a q -2 plus 5. You can say this one equals q then 3. So then this one equals 14. That means on this graph we have a point -2, 14. Okay, so here the reason we put -2, we try to get 3 here because we only know this point. If you put 3 here, that's 3 plus 5, that will be 8, q8. We don't know that value. So that's the reason we need to put -2 here. -2 plus 5 give us q3. So q3, we know that value, that's equals 14. So then that means in this graph, they have a point that's -2, 14. Now let's see this one. You need to x should be equals 15 because this one we need q that's 15 divided by 5. So this one equals q3. So this one equals 14. So that means in this graph we have a point that's 15, 14. Okay. Yeah, you can say here we put 15 just because use 15 divided by 5. This will give us 3 because we only know the value of q3. So then we can put 15 here. 15 divided by 5, that's 3. Then q3, we know that value, that's 14. Okay, so now let's go to problem 11. The graph of y equals fx is shown at the right. In this problem, we found the graph of y equals 2 times f -1 plus 3. So to get this graph, we can use these 3 steps. First, get the graph of this one. So how to get a graph of this one? Let me ask, Anticus, can you tell me how we can get the graph of fx1, fx minus 1. You know,
so
yeah, go ahead.
We can just graph y equals x minus 1.
How we can graph that?
So first, if we take the x value as 0, then the y value will be negative 1. And then if we take 1 as the value of x, then y will be 0. And then 2, and then 1, and then 3, 2, and so on and so forth.
So you see here, they already give you this graph. This one is y equals fx. Start from this. Can you find a shortcut to get a graph?
You can shift it downwards one. Upwards one.
Upward?
No, to the right.
Yeah, to the right side, 1 unit. So that means you do this. You say this point that's move to here. Move to 1 unit, okay? You move this one 1 unit. Then you connect these 2 points. Okay, that will be this part, this neck. Now this one you move the 1 unit to the right side. That's this one. This one you move the right side 1 unit. So this one's open. Okay, then you connect these 2 points. Okay, this red color, that's graph of y equals fx minus 1. Okay, you got this. So here minus 1, that means you need to shift the function graph of y equals fx to the right side 1 unit. Now b, find the graph of y equals 2 times fx minus 1. Now let's see, Brandon, can you tell me how we can get this graph, y equals 2 times fx minus 1? Use the graph of this red color. Can you tell me how we can get the graph of y equals 2 times fx minus 1 from the graph of y equals fx minus 1? How we can get that? Brandon, do you have any idea? No?
Oh no, I'm sorry. I'm not sure yet.
You're not sure, okay. Now let me ask Clara, can you tell me how we can get a graph of this function from fx minus 1?
I don't really know either.
You don't know either, okay. Lucy, can you tell me how we can get this?
Is it like double the size?
This one, 2.
Since it's 2?
Yeah. This one, you know, actually it's a stretch of the function on the vertical direction 2 times. So you just need a stretch. So how to do that? You just take this critical points. That's critical points that can order it, then y can order it, then times 2. Say for this one, that's -2, right? That's -1. This y can order it. This point, that's -1. -1, then times 2, you got a -2. So then now let me change color, use blue. That will be this point. That will be changed to here. Because this one's -1, then times 2. That will be go to -2. Now this point, consider it that's +2. Then times 2. That will go to +4. So that's 3, 4. That will go to here. This open. Now you just connect these 2 points from here to here. That will give you the graph of this segment. Now let's find the next one. This point, that's -1. Then we times 2. That go to -2. That go to here. Then this point, that's -1, 2, 3. That's -3. Then times 2. That will go to -6. 5, 4, 5, 6. That will be about here. Then you connect these 2 points. You connect these 2 points. Okay. This blue color, that's give you the graph of y equals 2. This one equals 2 times fx minus 1. Okay, you say this is called a stretch on the vertical direction. Now we already have the graph of this, graph of this. Now how we can get a graph of the final function, this one?
Do we just shift the blue function down by 3?
To which direction?
Down or
down? Plus, that means shift
up.
Shift the blue color function up 3 units. So then let me change this color to like green. Then you can just take this critical points. This one is -2 here. Shift up 3 units. That'll go to +1. That'll go to here. Then this point, that's -4, +4. Then shift 3. That will be go to +7. So about here, that's open. Then you connect these 2 points. Then you got this one. Now next section, the blue color, this one's -2. Go up. That will be +1 here. This one, that's -6. Go to here. Then you connect these 2 points. This one, that will be graph. Okay. The green color, that's graph of function y equals 2 times f x minus 1 plus 3. Okay, that will be this. You can see we can call the y equals fx, call this function parent function. We start from this function, then first we shift right side 1 unit, we get this one. This called children function, okay? Children function, because this function is produced from this one. Then 2 times this, with just the stretch of this function on the vertical direction 2 times. Then we got the blue color. This is the 2 times fx minus 1. Then this one plus 3, that's we just shift the blue color graph to the up 3 units. If this one's -3, that will be shift down 3 units. So you can say by this way, we can start from a very simple function, then we can graph a very complicated function. Just use the rule what we learned here. You don't need graph from the beginning. Okay, from beginning that's hard, but you just use the transportation way what we learned to shift or stretch, squeeze, then reflection, then you can get your graph of very complicated function. Okay, that's what we learned here. Now let's go to next section called transformation. So then now let's see section 3, inverse functions revisited. So we already show you the reverse function, right? Remember, if we have a function y equals like 2x plus 1, right? Then the reverse of this function, you just solve x in y, then you can get x equals y minus 1 divided by 2. Then you switch the variables. You change the x to y, y to x. You get a function that will be y equals x minus 1 divided by 2. So this function called inverse of this function. So you can say if you graph these two functions, there's symmetry about y equals x. Okay? If you graph the first function, this one's x, this one's y equals 2x plus 1. So the path, suppose this one's 1, then the slope, so this one's 1, slope that will be 2, then that will be here. When x equals 1, then y equals 3. So then you connect these 2 points. Okay, so this graph, that's y equals 2x plus 1. Then if you graph this one, then you got to say when x equals 0, y equals negative 1/2. Y equals negative 1/2. That will be somewhere here. Then when x equals 3, then y equals 1. It's 2, 3. When x equals 3, y equals 1. Okay. Then you connect these 2 points. Let's change the color. Something like this, right? Okay. Then you can graph the y equals x. You can say y equals x. That will be something like this. Okay. Then you can say the red color and the blue color, these two lines symmetry about this green color. This green color, that's y equals x. This green color function, that's y equals x. So then we know the original function and the inverse function, their symmetry about y equals x, about this line. And to calculate the inverse function, you just solve x in terms of y. After that, you switch the x with y. Then you get the inverse function. Okay? So now let's say this first problem, they give you fx equals 4x minus 3. They ask you to find the inverse function of fx. So everybody, you can do that on your scratch paper. You see, this one actually is very easy. You can do first, you can set this one's y. This suppose that's original function. That's y equals 4x minus 3. Then you solve x in y. You get the x will equals y plus 3 over 4. Then you switch the variables. You got y equals x plus 3 divided by 4. So this one, that's inverse function of this one. If you graph these two functions, you can see their symmetry about the y equals x. Okay, so I don't need a graph here. Then you already see the similar graph already. Now let's see 13. 13 is that let f be a function whose graph passes through the points. They give you these 3 points. Suppose f has an inverse. Name 3 points that must be on the graph of this inverse function. Okay, now let's say 3. Can you name 1 point? One of this cutout point? 3 is not here today. Let's say okay, E, can you name one of this point?
Maybe 3, 2.
Yes, that's correct. 3, 2. You just switch the x and y. Because
And
in the original function 2, 3. In the inverse function, that will be 3, 2. Okay?
And so will the rest be 7, 4 and 12, 8?
Correct. Very good. Yeah. That's these 3 points. That will be 3, 2, 7, 4, and 12, 8. You know why? Because see, the inverse function that's change the switch, change the x and y coordinate, right? So then you can say in the original function, this one's x. In the inverse function, that will be y. So that will be 3. This one will be 2. This one will be 7. This will be 4. Okay. So that's reason. Now let's see 14. Suppose we have the function f has an inverse. How the graph of y equals fx and y equals f negative x related? So actually I already show you their symmetry about y equals x. B, we saw earlier that we can use a vertical line test to see if a graph represents a function. Is there a test we can apply to the graph of function to see if a function has an inverse?
Is it possible to do like a horizontal line test to make see if it has an inverse?
Yes, you use a horizontal test. If you get the 2 for the same y value, you get the 2 more than 1 x value, then that means that function will not have the inverse function. Because if they have the inverse function, then they will have later they will have for the same x value, they will have the at least 2 different of y value. That would be not a function. So yeah, you're right. Use a horizontal line check. Let me give you an example. Suppose we have a original function. Suppose this one, y equals x squared. Okay. This one, if you graph this, one, you will get something like this. right? This is y equals x squared. Then, we know this one is a function, right? When we draw a vertical line, we only get the one intersection point. But now, if we check if this one have the inverse function, then you just horizontal line. Then you can say you have two intersection points. That means this function don't have the inverse function. If you try to get the inverse function, say solve x in y, in term of y, you get x equals square root of y, then plus minus. You got two values. One is square root of y, another is negative square root of y. So then you get two branches, right? Then that means this one cannot be a function. If you try to get this function, you need a limit x is greater or equal 0. That would be fine. But this way, then you can only get x equals square root of y, right? You cannot take this negative. You get this, that would be an inverse function. You can say, if we limited that one to here, then this one, I can change the color. The inverse function will something like this, okay? Then if you draw this, oh no, we need to use a line. You can draw, okay? You can say this branch, when we limit x greater or equals 0, we only have this branch, right? Then the inverse function, this one, that's y equals root x. When we solve x in term of y, we get x equals root y. Then we switch variables, get y equals root x. Then this graph, that's blue color. Then you can see this one and the y equals x squared, when x greater equals 0. There's symmetry about the y equals x. Symmetry about y equals x, about this line. Okay? Very good. To check a function, if it has an inverse function, you need to draw a horizontal line. Check. Okay? So then we finish this section. Actually, we also finished this chapter. Now let's see the summary for what we learned in this chapter. In this chapter, we learned the graphing of function, right? To graphing, the most important, start from the very simple function. We call that parent function. Then we start from there to do the transformations, like shift on the horizontal direction, left side, right side, vertical. Then we also can do the stretch, okay, and reflection. Then we can get a very complicated functions graphs. So to check if a function is if a graph is a function, you need to use a vertical line check. So if you can get more than one intersection point, then you can see here this says a very important, if we have a graph y equals fx plus k resulted from the shifting the graph of y equals fx vertically upwards by k units, while the graph of y equals f parentheses x plus k results from the shift the graph of the y equals x horizontally to the left k units. So if this one's plus, that's shift to the left side, okay? If this one's minus, that means shift to the right side k units. Now, graph of y equals k times fx resulting from scaling the graph of y equals fx vertically by a factor of k, while graph of y equals f parentheses k times x, resulting from the scaling the graph of y equals fx horizontally by a vector of 1 over k. Okay, so if this one is greater than 0, that means horizontally that would be switch. Okay, now let's say graph of y equals negative fx. That's a result of the flip of the graph of y equals fx over the x-axis. If you try to get the y equals negative fx, you just flip the graph of y equals fx over the x-axis. If you try to graph of y equals f negative x, this one is just a flip of the graph of y equals fx over the y-axis. Okay? Pay attention to here, okay? If you try to graph y equals f negative x, you just flip the graph of y equals fx over the y-axis. If you try to graph the y equals negative fx, you just need flipping the graph of y equals fx over the x-axis. So if we try to graph the inverse function of fx, then the graph of y equals inverse of fx, it's a reflection of the graph of y equals fx over the line x equals y. So that's actually the y equals x. So that means you just reflection of the y equals fx over the y equals x. That means the graph of original function and their inverse function is symmetry about y equals x. A function has an inverse if and only if there does not exist a horizontal line that pass through two or more points on the graph of the function. So that means if you try to check if a function has an inverse function, you just need to draw a horizontal line, check if this line has at least two intersection points with this graph. If you have two or more, that means this function don't have inverse function. Okay, so now let's go to next chapter, polynomials. Polynomials that play a very important role in the algebra and also in a lot of mathematical branches. Now let's see what is a polynomial. You know, actually we already access a polynomial many times. You know, like quadratic equation, quadratic function. That's also a polynomial. Like x squared plus 5. This is a polynomial. You can also write like ax squared plus bx plus c. This is a polynomial. So what is a polynomial? Polynomial, that means you have one variable, at least have one variable. Okay, you can also have more than one variable. Then they're the sum of the terms in which each term is a constant times a variable, then raised to a non-negative integer power. So you have these powers. The power should be non-negative. You cannot like this, like x power negative 2. Then like plus 1. This one is not polynomial. Because this one, we can write this 1 over x squared plus 1. This one will equals x plus 1 plus x squared over x squared. This is a fraction function. This one is not a polynomial. Polynomial require the power of the variable should be non-negative, should be greater or equal 0. Okay? But for the constant coefficient, that can be a fraction like this. 1/8, that's coefficient of x power 3. Negative 1/8, that's coefficient of y power 3. This one is still called polynomial. But we only require the exponents of the variable should be non-negative. Like this kind of function, this one, they are not polynomials. Because see, this variable, the power actually is -1. This one, that's also -1. This one, you know, the power, that will be have a squared plus b squared, then power 1/2. Okay, because this 1/2, we cannot call this one the polynomial. If we don't have this, they'll have a squared plus b squared. This one's a polynomial. Okay, if a and b are variables, you know, this one is also a variable. It's a polynomial. They have two variables. Okay, so the highest power of a polynomial, that's called the degree of the polynomial. Okay, that term also called the leading term. So you can see here, the grid of this polynomial, that's 5. Because the highest exponents in this polynomial, this one's 5, here that's 2, right? The highest, that's 5. So the degree of this polynomial, that's 5. And the x power 5 called the leading term. This one called the leading term. Okay? So then you can say this one, the degree of this polynomial, that's 9. The leading term, that's t power 9. This one, that's degree, that's 10. The leading term, that's -8 z power 10. Okay? Now, if you have two variables, like this one, you need to add the degree of each variable in one term together, then compare which one is the highest. See here, z squared, the degree of z, that's 2. Y, that degree, that's 1. 2 plus 1, that's 3. Okay, this term, the degree is 3. This term degree, that's 2. This one is 3. So among all these terms, the highest, that's this one and this one. Okay, so then the leading term, you can say this one or this one, but the degree, that's 3. Now let's see the coefficients in the leading term, we call the leading coefficient. You can say 3x power 4. This degree, that's 4. That's highest in this polynomial. Then 3x power 4, that's leading term. Then this 3 we'll call leading coefficient. Leading coefficient, that's 3. Okay. Then if the leading term is 1, then the polynomial is called monic polynomial. Okay, if this leading coefficient equals 1, this polynomial called monic polynomial. Okay, the last term, you don't have the variable like this, -7, this is called a constant term. Okay, now let's see what we learned, quadratic function, that's also a special of polynomial. Then definitely this power can go to higher, 3, 5, or whatever. Then that's still a polynomial function. Now let's see general. The general term of a polynomial of degree n, you can write like this. This is a general form. of a polynomial of degree n. Okay, now let's see addition and subtraction. First problem, they give you fx is this function, gx that's this one. Then they ask you add these two functions. This one will be very easy. You just add their next term together, right? So now let's say Brandon, can you tell me what is the sum of f and g? If we add f and fx and gx together, what's your answer?
Negative x to the third minus, minus 3x plus 2x squared.
How you got that?
What?
How you got that?
Because I just added it.
Can you show me how you add? You write this one, this term, add this term equals what?
Negative 2x squared, f to the third.
X negative, okay, good. Then second term.
Plus 2x squared.
Plus 2x squared, okay.
Yeah.
Third one, this negative 4x plus x.
Yeah, minus 3x.
Minus 3x, okay. Then
And
positive 7 and negative 7 cancel out, right? So the answer is this, okay? Very good. Now, then fx minus gx, what do you get?
Wait, you're asking me still?
Yes.
Okay. 4x to the third.
Okay.
Plus minus 2x squared.
Yeah, minus 2x squared, okay. Then?
And minus 5x.
Okay.
And minus 14.
Correct, very good. Okay, so C, for what constant C does the polynomial fx plus c times gx have degree 2? Okay.
Mr. No. Isn't it plus 14 for B? Because 7 minus negative 7?
So then they ask you, what is this constant C? Can make this one equals degree 2.
No, I meant for B. You said minus 14. It's supposed to be plus 14, I think, because it's fx minus gx is 7 minus negative 7. For B.
That for B, what I read here is wrong?
Yes, I think it's supposed to be plus 14 because it's x.
Oh, yeah, right. Yeah, this one's plus 14. Right, yeah, 7 minus negative. Okay, good. Okay, that's correct. So, Brendan, can you tell us what's the answer for C?
I'm not sure on that one.
Okay, let's see. No C. What's your answer for the C? See, for what constant C does the polynomial fx plus c times gx has a degree 2? No C. Do you have an answer for this? Is no C not here? Now let's see. Clara, what's your answer for C? Okay, E.
I think for C,
Yeah.
the constant C would have to be 1/3 because in order for fx plus gx to cancel out the term x cubed and negative 3x cubed, we will need to divide negative 3x cubed by 3 to get the negative x cubed, and x cubed plus negative x cubed would cancel out,
Yes.
leaving 2x squared or 2/3 x squared being the leading 2/3 being the leading coefficient,
Right.
and 2/3 x squared being the leading term,
Yeah.
and 2 being the degree.
Right. You use 1/3 times gx. By this way, you cancel out the leading term. Then the degree of these functions will lower. There will be the leading term will be x squared. So you do this. Then you say this one x power 3 minus 4x plus 7. Then minus x power 3. Then plus 2/3 of x squared. Then plus x over 3. Then minus 7 over 3. But this one say x power 3 will cancel out. Then the leading term, that will be this one. So they'll have degree 2. Okay, very good. Now let's see number 18.2. Is the sum of two polynomials always a polynomial? Antiquus, can you answer this? Is the sum of two polynomials always a polynomial?
No, because if we have one polynomial which is negative 2x plus 7, and we added it with 2x squared,
This one
2x plus 2x minus 7,
okay.
that would just equal 0, which is not a polynomial.
Is 0 is not polynomial? 0 is also a polynomial. Okay, based on the definition, you can see general form of a polynomial is this: fx equals an x power n, then plus an minus 1 x power n minus 1, then blah blah to a1 x power 1, then plus a0, right? This one, that's actually that you don't need to write this, okay? But I try to show you here. You can say we require only like these powers should be greater or equal 0, right? That's the only requirement. Then if we set this n, this all the the coefficient that's from a1 from a0 a1 to an, we set this one all equals 0. This one all equals 0. Then what we get, this one will equal 0. So that means 0 is also a polynomial, but definitely it's a very simple and very boring polynomial, right? But
so is every whole number a polynomial?
Yeah, you
So
can say
then
any number.
The answer to that question would be yes.
Yeah, the answer for this one, that's yes. Yes, all the sum of the polynomials always polynomial. This one's true. Now let's see number 3. Suppose fx, gx, and hx are polynomials such that hx equals fx plus gx. Is it possible for degree h to be larger than the both degree of f and g? Let's say who can help me answer this question? Brandon, can you answer this question for me? Is it possible for degree h to be larger than both degree F and G.
Yeah,
Can you give me an example?
like if degree F and degree G are both positive, then it's, yeah.
Can you give me an example? You mean the, say, I'll give you an example. Suppose fx equals x squared and gx equals x. So then hx will equals fx plus gx. Then that will equals x squared plus x. So then what's the degree of hx? Brandon? Tell me what's the degree of gx? Say here you can say degree of fx, this one equals 2, right? Degree of gx, this one equals 1, because this power that's 1. Then you can see here degree of h function, that's still 2, right? They did not greater than the degree of f. It's greater than degree of g, but it did not greater than both of them. E, do you have any question for this problem?
No, I was going to solve it.
Okay.
But I can solve part B.
Okay, so then what's your answer for B?
Oh, B, we just proved it in like one of the other problems, and that answer is yes, because it's possible for the degree for for f, say f to be like say 3, and the degree for G is also 3. But say f is like the leading terms of f is say 3x cubed, and G is negative 3x cubed. They cancel out, and it's smaller.
Correct, you're right. So say for A, this one is wrong. Okay, this one is not possible. The sum of these two polynomials, the degree can only equals one of them. You cannot greater than both of them. You can only greater than one of them. You cannot greater than both of them. Okay? But for B, this one's true. It's possible. You know, we already showed you in the previous problem, you know that two functions, their grid are 3. Then we found that the C equals 1/3. Then we use that 1/3 times gx, then later make the function cancel out their leading term, make the leading term becomes 2 x squared. Then their degree, the degree of this hx become 2, but the degree of f and g are all 3. So B, that's correct, but A, that's wrong. So now let's say we finished the first section. Now let's go to multiplication. So here the multiplication, that means multiplication of the polynomial. Okay. Then how you can do the product of these two polynomials? To do that, you just use vertical formula, just multiply. That's you. Also, you call the FOIL. Okay, use this FOIL. Okay, this rule to do this multiplication. Plus y minus 7 times 3y squared minus 2y plus 3. So do this multiplication, you know, use this one times this, you get a 3 power y power 5. Then this one, that will be minus 6y power 4. This one, that will be plus 3y cubed then minus 21y squared. Okay, then you use negative 2y times y cubed, then you get this one right, negative 2y power 4. Write down this, the like terms, just align them, okay, make that on the same column later because we need to merge them. So then here that's negative 2y times negative 2y squared, that will be plus 4y cubed. Then this one, that will be minus 2y squared. Then this one will be plus 14y. Okay. Then 3 times y cubed, get 3y cubed. Then minus 6y squared. Then plus 3y. Then minus 20y. Okay, so then we draw a horizontal line. Then we add this to negative 21. Then this one will be 17y. Here that's plus. Here that will be negative 21, negative 2, and negative 6. Give us negative 29 y squared. Then here that will be 10y cubed. Then here that will be minus 8y power 4. Then this one will be 3y power 5. Okay, so this is a way for you to do the multiplication. Okay, multiplication, you can write the multiplication sign here. These two polynomials. You already write the higher degree of the polynomial on the top. Write the lower degree on the bottom. This one will be a little bit easier. Then write the like terms on the same column. Then later that's easy for you to merge. Then write all the terms from the highest degree to the lowest degree. Then you get the answer for this one, that will be this. Okay. Now let's see. Must the product of two polynomials always be a polynomial? Okay. Let's say let's see, we still have Clara, are you still here?
Oh yeah.
Can you answer this question? If we multiply the two polynomials, do we still always get another polynomial? You say, must the product of two polynomials always be a polynomial?
Yes.
Yes. Can you explain why?
Because when you multiply it all out, like no matter what, it's always gonna add or subtract into 1.
Yes, correct. This one's true. Very good. So for polynomial, you can say add, minus, plus, minus, multiplication, always still give you the polynomial. Okay. Then now let's see number 6. Suppose we have fx and gx are non-zero polynomial and hx equals fx times gx. How is the degree h related to the degree of fx and gx?
Can I answer?
Yes.
I think the degree of h is just the sum of the degrees of fx and gx.
Correct. Just add the degree of f and gx together. That will be the degree of hx. B. If fx and gx are monic, so that means leading coefficient, that's 1. Must hx be monic as well? Let me ask Anticus. Anticus, can you answer this question?
Question C.
Question B.
fx and gx are monic, meaning they're leading terms of coefficient 1,
Yes.
must hx be monic as well?
Yeah. Is this one true or false?
I believe it's true.
Do you know why?
Because if you have say x to the power of 2 times x to the power 3, that'd be x to the power 5. And it works with every other variable and every other power.
Yeah, that's true. Time is up. We can stop here. Then your homework, that will be exercise problem behind each section, and also the review and challenge problem in the previous chapter. Okay, we can stop here. Next time we can continue.